All right, so this is the last part of section 12.5, and we are going to be looking at how to measure the distance from a point to a plane, and also how to look at the distance between two parallel planes. So let's take a look. Let's start with measuring the distance from a point to a plane. Okay, so take a look at the picture below. Let's say we have some point sitting above or maybe sitting below a plane. We'll call it P1. I'm going to let the coordinates of that point be x1, comma y1, comma z1. And let's say that we have some point sitting on the plane. We'll call it p naught. And let's say the coordinates of that point are x naught, y naught, z naught. This will lead into our formula we're going to see in a little bit. So just to get some setup. Okay. What we're interested in is we want to measure the distance from this point P1 to the plane. And if you remember from, well, maybe it's been a while, but from geometry class, one of the biggest postulates in all of geometry is talking about how do we measure the distance from a point to a line. So if I have some point sitting here and I have some line underneath, what's the correct way to measure the distance from the point to that line? And the answer is that you have to measure it perpendicular to that line. So we measure the distance perpendicular from the point to the line. Works the same way with a plane. So what I want to do is I want to measure the distance from P straight down at a right angle to the plane, which means I'm going to be moving in the direction of that normal vector, which you see outlined here. Originally it was in pink, but now I'm overlapping it in blue. There's my normal vector. So what I'm really interested in figuring out is what's this distance up here from P1 down here to this pink point. I'll call it, it doesn't really matter what I call it. I'll just call it P. Okay. So that's D. I want to figure out D. Well, the way that we go about doing that is we really focus on this vector P naught, P. So we're looking at the vector that starts at P naught and moves in the direction of P. And what we're going to do is we're going to project that pink vector P naught, I'm sorry, P naught P1, not P naught P. Okay, so this purple vector, pink vector, I'm going to project P naught P1, which, to make labeling easier, let's just call that vector B. I want to project that vector onto the normal vector, and I want to measure the size of that scalar projection. Okay? So it helps if you actually have the vectors start from the same point. So I'm going to redraw this off to the side. Then it'll look more in line with what we discussed in section 12.3 when we talked about projections. So here's P naught, here's P1. And I'm just going to, all I'm going to do is I'm going to pick up this, I'm going to highlight, I'm going to take this vector, I'm just going to shift it over to the left and put it here. Okay, so all I'm going to do is just going to put this vector here instead. And slide to the left. That was a cheesy attempt at humor. Hopefully some of you left. Okay. So here's my normal vector here in blue. That was n, right? And this is the distance we're trying to measure here, which is d. And I'm just going to throw this angle between the two vectors here. So here's our angle theta. Okay. And so this vector P naught P1, there's B. We want to measure D. And so what we're going to do is we're going to project vector B onto the normal vector. And what that's going to do is it's going to give us this length, D. Okay? It's going to end up giving us the scalar projection of B onto N. Okay? Absolute value we need because we want it to be positive. Remember, the scalar projection, depending on which way it points, could give you a positive magnitude or it could give you a negative magnitude. Since we're talking about distance, we need the quantity to be positive. So just to kind of get things started here, let's just write some stuff off to the side. The distance from the point to that plane is going to be the scalar absolute value of the scalar projection. Remember, the way we abbreviate that is COMP. It's the component of B along N. Okay. Using our definitions, that would be the absolute value of the dot product of N dotted with B divided by the magnitude of N. I don't need to put that inside the absolute value bars because that quantity has to be positive. It can't be negative. And we can expand this a little bit. We could really go straight from here. But let's kind of do a little bit of work here. We can actually, what we're going to end up with is we're going to end up with this formula, but let's see where we get that. So the distance d from the point P1 to the plane, let's say that this plane in blue up here is given by the equation ax plus by plus cz plus d equals 0. Okay? If we want to measure the distance from P1 to that plane, let's start here and see how we can work our way to what we have down here. Let's say that the normal vector has components, I'm just going to call them A, B, and C, okay? Which I know because the plane that I'm measuring to has coefficients A, B, and C. So that's going to be the coefficients of my normal vector. And I know vector B, if this coordinate P naught has coordinates x naught, y naught, z naught, and this coordinate P1 has coordinates x1, y1, z1, then vector B would be given by the difference in those coordinates. So x1 minus x naught, y1 minus y naught, z1 minus z naught. And so I'm going to take the dot product of these two vectors and take the absolute value. So what I'm going to get, if I come, see where I have space, I'm going to come over here. So I get absolute value of A times x1 minus x naught plus B times y1 minus y naught plus C times z1 minus z naught over the magnitude of n would be the square root of a squared plus b squared plus c squared. And so you'll see it's kind of getting closer to what we want. So let's see. If we decide to combine some like terms here, I'm going to pair up everything that has a subscript of 1 together. So I end up with, where do I have space? Absolute value of a x1 plus b y1 plus c z1 minus quantity a x naught plus b y naught plus c z naught. I'm factoring the negative sign out from the last 3 rounds of distributing. This is still over the square root of a squared plus b squared plus c squared. And this is the part where you have to think about the plane that they gave you. This quantity right here, ax naught plus by naught plus cz naught, is looking at the plane that we're measuring to, and what point do we know that sits on that plane? P naught. What are the coordinates of P naught? X naught, y naught, and z naught. So we just plugged in coordinates of P naught into that plane, which means this quantity right here is going to become ax naught plus by naught plus cz naught. And that's what we have right here. So if we solve for that quantity and move d to the other side, this quantity right here just turns into minus d. Well, if we pair up minus minus d, we end up with positive d. And so really, we can reduce all of this to just what we have here in yellow. The distance from the point P1 to the plane is given by the absolute value of ax1 plus by1 plus cz1 plus d. So take your ordered pair that they give you and plug it into the equation of the plane that you're measuring to, and then divide by the magnitude of that normal vector. So divide by the sum of the squares of the coefficients of x, y, and z. Okay. In order to use that formula, you got to make sure the plane is written in this form, ax plus by plus cz plus d equals 0. So make sure that you have 0 on one side. Okay. And we can apply this logic also to the distance between two parallel planes. So let's say we wanted to find the distance between the two planes x plus 2y minus 2z equals 3 and 2x plus 4y minus 4z equals 7. First thing you should be asking yourself or confirming for yourself is how you know these are parallel. And I can tell that because of their normal vectors. The normal vector for the first plane is 1, 2, negative 2. And the normal vector for the second plane is 2, 4, negative 4. And so I can see that the second normal vector is exactly twice as large as the first normal vector. N2 is equal to 2 times N1. So that confirms for me that the planes are parallel. They didn't ask us to check that, but it's always good to ask yourself why that works. Okay. So what's our strategy going to be? We don't have this separate formula for measuring distance between planes, but we can pick a point on one of those planes, and we can measure the distance from the point on that plane to the second plane. It does not matter what point we pick as long as the point is on the plane. Okay. So our strategy, it always helps to have a strategy going into these problems. Strategy is going to be to pick a point on one plane. It does not matter which plane you pick. This process works regardless of the starting plane. On one plane. And then you want to measure the distance to the other plane, to the second plane. So I'm just going to go in order of the planes that they gave us. It should be usually fairly easy to pick a point on the plane. If you plug in 0 for a couple of the coordinates, it should be pretty obvious a point on one of the planes. So, for example, if I let x equal 3 in the first plane and I let y and z be 0, then I get 3 equals 3, which is a true statement. So I know that 3, 0, 0 is on the first plane. And so what I'm going to do is I'm going to measure the distance from that point, 3, 0, 0. So we're going to measure the distance, we'll call it d, from the point 3, 0, 0 on the first plane to the second plane, 2x plus 4y minus 4z. Remember, we got to have 0 on one side, so I'm going to subtract 7 over to the left. Minus 7 equals 0. And so all I'm going to do now is I'm going to take 3, 0, 0 and plug that in for x, y, and z and use my formula from up top. So the distance d, let's call this step 2, is going to be the absolute value of taking 3, plugging it in for x, and then taking 0, plugging it in for y and z. We end up with 2 times 3 plus 4 times 0 minus 4 times 0 minus 7. We need the absolute value in order to make this quantity positive, divided by the magnitude of the normal vector. Now, we have two normal vectors, so you got to ask yourself, which one are we using? It's the normal vector of the plane that you're measuring to. We took a point off of this first plane, but that's not the plane we're measuring to. We want the normal vector of the second plane because that's the plane that we're measuring to. So I want to be dividing by the magnitude of n2. So square root of 2 squared plus 4 squared plus negative 4 squared. Okay. Kind of have to think visually a little bit about what you're doing so you're not just memorizing formulas. You want to know where are you starting, what point are you starting at, and what plane are you measuring to. So I get absolute value of 6 minus 7 would be negative 1. So absolute value of negative 1 over the square root of 16 plus 4 would be square root of 36. And so the distance from that point to the plane is 1/6. And therefore the distance between those two parallel planes has to be 1/6. And also one more point of clarification. We did not have to pick the point 3, 0, 0. As long as we pick a point that lies on this first plane, as long as it makes a true statement, we would have gotten the same result. Doesn't matter what point on that plane I pick. So there's my distance, 1/6. Okay, let's look at one more example. Yesterday in the last video, we showed that these lines below are skew. This was example, let me take a look real quick. Maybe it was 2 days ago. I think I've made 3 videos for this section so far. It's a longer section. I think it was section 12.5 day. Yeah, it was 12.5 day 1. So take a look back at the last example. You need a recap. This was from the last example of 12.5 day 1. There's a video to go along with that on the channel. We took these two lines given parametrically, and we showed that they were skew lines. We ruled out that they were parallel. We tried to check for an intersection, and what we ended up finding was that the x and y coordinates matched, but they had different z coordinates. These two lines had different heights. So unfortunately, the lines did not intersect, but they were not in the same plane. They weren't parallel, so they had to be skew. That's the short spoiler of the longer process that we did a couple days ago. Go back and check it out if you need a recap. So we know they're skew, and we can measure distance between skew lines. And the reason we can measure that distance is because skew lines are non-coplanar. They lie in parallel planes. So for example, if I sketched you a picture here, I think I drew this exact same picture a couple days ago. Let's say I wanted to measure the distance. Let's say this was L1. Not saying that this is drawn completely accurately, but let's say that was L1, and let's say this was L2 down here. These lines lie in different planes, but the planes happen to be parallel. Okay. Plane on the top and the plane on the bottom are parallel planes. The lines are skew. They don't move in the same direction, but they also don't intersect. So they're not parallel. They're skew. There's L2, maybe. If I want to find the distance between those lines, it's the same as finding the distance between those two parallel planes. Okay. So it helps to view these lines as lying on two parallel planes. That's a fun fact about skew lines. They lie in parallel planes. So if you compute the distance between the lines, it's the same as just computing the distance between those two planes. I would put a star next to this, draw a puppy next to it. Okay, I'll draw a puppy next to it. That's my best version of a puppy. It's cute, right? Yes. Okay. One thing I'm going to do, I wrote the direction vectors the other day next to these lines. I'm going to do that again. The direction vector for this one was 4, -4, 5. Remember, it's just the coefficients sitting next to the parameter. The direction vector for this line next to S, I see 8, -3, and 1. Okay, we're going to need those direction vectors. You'll see in a bit. Okay, so following the process I did in the last example, if I want to find the distance between two parallel planes, I'm going to need a point on the first plane. So let's just say line 1 sits on one plane. I'm going to need to take a point on L1, and I'm going to have to measure the distance to the plane containing line 2. Or you could reverse the roles. You could pick a point on line 2, and you could measure the distance from that point on line 2 to the plane containing L1. It does not matter which line you start with and which line you end with, but you have to start with a point on one line and measure the distance to the plane containing the other line. So we need a point and a plane. Okay, so strategy. Go into these problems with a plan. I'm going to just say use line 1. Okay, again, it doesn't matter which line you start with. Use line 1 to find a point on that line. And then use line 2 to write the equation of the plane containing that line. Line 2, to be specific. Then calculate the distance from the point to that plane. You'll have a point, you'll have a plane equation, you can plug into the formula that we saw on the last page. Again, I'll mention it, you could also reverse the roles of L1 and L2. Does not matter. Okay, picking a point on line 1 is fairly straightforward. You can let t be any value that you want. I just usually would let t equal 0. If I let t equal 0 for line 1, then clearly the point 1, 5, -1 lies on L1. So step 1, I'm going to say if we let t equal 0, then 1, 5, -1 gives a point on L1, and we need that. Okay, so then I would say the longest part of this process is going to be coming up with the equation of that plane. Hey, we need an equation of the plane containing line 2. So you should be asking yourself, use the building blocks that you already know. Okay, what do I need to write the equation of a plane? I need a point on that plane, and I need a normal vector to that plane. Okay, well, getting a point on the plane would be the same as what we did for the first step. Let's plug in s equals 0 and figure out a point containing line 2. If line 2 is in the plane, then the point's going to lie on line 2, and it's going to lie in the plane that we're looking for. So if I let s equal 0, clearly the point 2, 4, 5 is going to lie on line 2, and therefore it's going to lie in the plane that we're going to write the equation of. So if we let s equal 0, then the point 2, 4, 5 is a point on line 2. And so now we just need a normal vector to that line, or a normal vector to the plane containing that line. Well, we have the direction vectors of both of these lines. So if I want a line that's going to be perpendicular to that direction vector, I could just take the cross product of both direction vectors. Then I'm going to find a normal vector that's not only perpendicular to V2, but it also happens to be perpendicular to V1. I don't really care about that second property as much, but it's a nice added bonus. What I really care about is that it's going to be orthogonal to V2. Because V2, remember, what is V2? V2 describes the direction of this line right here. And I want a vector perpendicular to that to describe the plane. Okay. So a normal vector n for L2 is given by the cross product of the two direction vectors of the lines, V1 cross V2. So setting up my determinant, ijk, V1 had coordinates 4, -4, 5, and V2 had coordinates 8, -3, 1. So we end up with I times, crossing off first row, first column, we're left with -4 times 1 would be -4, minus -3 times 5 would be minus negative or plus 15, minus j, remember to flip the sign, cross off first row, second column, we're left with 4 times 1 is 4, minus 8 times 5 is 40, plus k, times, cross off first row, third column, 4 times -3 is -12, minus 8 times -4 is -32, minus -32 would be positive 32. So we end up with 11, positive 36 when we distribute the negative sign, and 20. Okay. So there's our normal vector. I'm going to highlight the important pieces from step 2. There's our normal vector. There is our point. So I'm going to put these in green. Okay, now we can write the equation of the plane containing line 2. Okay. Remember how to do that from last video? You're going to take the dot product of the normal vector, 11, 36, 20, with the vector x minus 2, y minus 4, z minus 5. Because those vectors are orthogonal, their dot product has to be 0. So I get 11 times x minus 2 plus 36 times y minus 4 plus 20 times z minus 5 equals 0. Let's see what we get. 11x plus 36y. This one has some large coefficients. Plus 20z. Negative 22 minus 144 minus 100 would be minus 266. And obviously on a quiz or a test, you're going to have a calculator. You could do a lot of these larger products by just plugging them into your calculator. You don't have to do them by hand. Okay, well, now we have a plane. Okay, so here is our plane. Okay, and now what points are you going to use? There's a lot of different things going on here, so you need to be thinking about all the different pieces that we're doing here. The point that we're measuring from is the point that's not on the plane. So we don't want to use 2, 4, 5 as our point. The distance from that point to the plane is just going to be 0. This point lies on the plane. So we need to go back to step 1. This was the point sitting off the plane. It helps to draw a little visual for yourself. Here's 1, 5, -1. We want to measure that perpendicular distance. Here's line 2. We want to measure that perpendicular distance from that point to the plane. Okay. Using the normal vector that we just found, which was 11, 36, 20. So last step is we want the distance from the point on the first skew line, which was 1, 5, -1, to the plane containing the second skew line, which was this. Okay. And I like that format because it's got 0 on one side, which we need. So all we're going to do is we're going to replace x, y, and z with 1, 5, and -1. Absolute value of 11 times 1 plus 36 times 5 plus 20 times -1 minus 266, absolute value, divided by the magnitude of the normal vector to that second plane that we found. So we're going to want to use the normal vector 11, 36, 20. Square root of 11 squared plus 36 squared plus 20 squared. There you go. Cranking this out, let's see, 11 plus 36 times 5 minus 20 minus 266 gives me negative 95. So take the absolute value, we get positive 95. For the bottom, 11 squared plus 36 squared plus 20 squared gives me 1817. Square root of 1817. Most problems would ask you to leave it in exact form, so I'll do that here. If you are interested in knowing how many units that is as an approximate answer, just for the sake of interest, let's plug that in. 95 divided by the square root of 1817. It's not too far. It's about 2.229. Again, on a quiz or a test, it will specify what form it wants. Okay? So from this section, what have we done? We've looked at how to measure the distance from a point to a plane, which allows you to do a lot of different things. It opens up your world to different types of problems. You can measure distance between two parallel planes. You could measure distance between two skew lines because you can view them as lying on parallel planes. So there's a variety of different types of problems you can do just from that first skill. Okay. All right, that should give you enough to work on some homework. Happy mathing.